Hi again, it's Perry from Math Together Canada, and welcome to part 3 of our AMC 10A series with our awesome guest, Prince Zhang. In this video, Prince will be working through questions 16 to 20, some of the most interesting and conceptually rich problems on the contest. Follow along and see how he approaches these more advanced challenges.
Now, problem 16. All of the rectangles in the figure below, which is drawn to scale, are similar to the enclosing rectangle. Each number represents the area of the rectangle. What is length AB? So this is a rectangle, so let's set some variables. Let's let this shorter side be x, and this longer side of the rectangle with area 1 be y. So now since they're similar, we can infer that this is equal to 3x, this is equal to 3y, and so on. And so now let's try to find the length AB. This is the longer side, so it will be corresponding to y. So it will be equal to y root 32. This is the shorter side, so it's equal to 5x. This is also the shorter side, so it will be 7x. Now this is the shorter side, so this will be 6x. This is the shorter side, so it will be 4x. This is the longer side, so it will be y root 8. And this is also the longer side, so it will be y root 18. Now since the large rectangle is also a rectangle, these two lengths are equal. Let's label the rest. Let's label the C and D. So AB is equal to CD. And so 12x plus y times 4 root 2 is equal to 10x plus y times 5 root 2. So now we get 2x equals y root 2. So x root 2 is equal to y. Now since we know that the area of this rectangle is 1, we have another equation, xy equals 1. Now we plug y in to get x squared times root 2 equals 1. And so x equals 1 over the fourth root of 2. And so now we can solve for AB. We plug this back to find y. So y is equal to the fourth root of 2. So now AB is equal to 12x plus 4 root 2 times y equals to 12 over fourth root of 2 plus 4 root 2 times the fourth root of 2. And so this is equal to 6 times the fourth root of 8 plus 4 times the fourth root of 8. Which gives 10 times the fourth root of 8. So our final answer is D. Now, problem 17. Two teams are in a best 2 out of 3 playoff. The teams will play at most 3 games, and the winner of the playoff is the first team to win 2 games. The first game is played on Team A's home field, and the remaining games are played on Team B's home field. Team A has a 2/3 chance of winning at home, and its probability of winning when playing away from home is P. Outcomes of the games are independent. The probability that Team A wins the playoff is half. P can be written in the form half of n minus square root of n, where m and n are positive integers. What is m plus n? So what are the possibilities of Team A winning? Well, they could sweep the series in AA, they could win the first one but lose the second one, and then finally win game 3, or they can lose this first one and then reverse sweep. So now we can calculate the probability of each. This has a probability of 2/3 p. This has a probability of 2/3 p times 1 minus p. And finally, the reverse sweep has a probability of 1/3 p squared. So now if we sum this up, this should equal to half. So now we collect like terms. Now using the quadratic formula, we can solve for p. Now, since p is a probability, p must be between 0 and 1 inclusive, and so we can collapse this plus minus sign into a minus sign, since 4 plus root of 10 would be greater than 2. So finally, here's our answer, and we have m equals 4 and n equals 10. So m plus n is equal to 14, so our answer is E. Problem 18. There are exactly k positive integers where 5 is less or equal to b less or equal to 2024, such that the base b integer of 2024 is divisible by 16, where 16 is in base 10. What is the sum of the digits of k? So let's rewrite 2024 in base b as a base 10 integer. Now since we want it to be divisible by 16, we can write this as a modulo statement. Since all of them are divisible by 2, we can reduce the mod to a mod 8. Now we have two cases. First, let's consider the case where b is even. If b is even, then b to the power of 3 is divisible by 8. So we can cross this term out. So we're just left with b plus 2 is equivalent to 0 mod 8, which means that b is equivalent to 6 mod 8. Now we can check this with our assumption that b is even to find that this does work. And now, if b is odd, then b squared, we can do some casework, is always equivalent to 1 mod 8. We can see 1 squared is equivalent to 1. So since b squared is equivalent to 1, we can replace b cubed with just b. Now we can reduce the mod again. So now we get b is equivalent to 3 mod 4, which implies that b is equivalent to 3 or 7 mod 8. Now we can check back with our assumption that b was odd to find that they both work. So now, how many values of b are there? Well, for every 8 numbers, the numbers with remainders 3, 6, or 7 when divided by 8 work. Now we see that 2024 is actually divisible by 8. And so there are exactly 2024 over 8 cycles. So if we do some quick math here, you get 253 cycles. And so since there are 3 of each in each cycle, we get 253 times 3 equals 759. However, b starts at 5 because there's a digit 4, which implies that b is greater than or equal to 5. So we have to remove 1 for the 3 we counted in the first cycle, where b equals 3. So we remove 1, and we get 758. Now we want the sum of digits, so we'll just add it up, and equals 20. So our answer is D. Now problem 19. The first 3 terms of a geometric sequence are the integers a, 720, and b, where a is less than 720 and is less than b. What is the sum of the digits of the least possible value of b? So to get the least possible value of b, we want integers x and y, where x and y are both factors of 720. We want to minimize the ratio y over x while it's still greater than 1. And we will get the smallest value of b, which is 720 times y over x. So to find these, we can do some light bashing and just find all the divisors. And now as you're getting to the end of the bash, you can multiply this with the earlier divisors to make 720 instead of counting through each possible value. So for example, here 240 is with 3, so we know the next one multiplies with 2 to get 720, so it's 360, and finally 720. So ideally, y and x should be consecutive, and so we see that the largest pair of consecutive is here, 15 and 16. We can also try a few other ones, but in the end we do get that 16 over 15 is the minimum value of y over x, where y over x is greater than 1. So we can find b by multiplying by 720, and we get 768. So we want the sum of digits again, so we just add these up and we get E, 21. And now, finally, for the last problem in this video, problem 20. Let S be a subset of the numbers between 1 and 2024, such that the following two conditions hold. If x and y are distinct elements of S, then their absolute difference is greater than 2, or at least 3 since they're integers. If x and y are distinct odd elements, then their absolute difference is at least 6. It asks, what is the maximum possible number of elements in S? So first we can try greedily choosing numbers. So let's start with 1, and then the next one will be 4. And then we want the next one to be 7 since it's 4 plus 3. But then 7 is odd, so it doesn't hold for this rule. So we choose the next one, 8. After 8, we choose 3 again, 11. And we see that this does work because 1 and 11 are more than 7 apart. And then we continue doing this. And we find that every 10 numbers, there are 3 numbers that appear. The ones with remainders 1, 4, and 8 when divided by 10. So now we see that when this series ends, it will end at 2024, which is a very good indication that this is the best possible series, since it includes both the first and last number. So now we'll count how many numbers there are here. So every 10, there are 3 of them. So if we go from 1 to 2020, there are 2020 times 3 over 10 equals 606 numbers. And now finally we can add 2021 and 2024 to make 608. Now before we lock it in, we should try to find other sequences. And it just so happens that there are none, and so this would be our final answer, part C.
That's a wrap on part 3. Thank you, Prince, for sharing such great insights as we tackle these tougher problems. Don't miss the final part where Prince will take on questions 21 to 25, the most difficult ones of the entire AMC 10A. And remember, we'd love to feature you next. If you enjoy explaining math or solving problems, reach out and let's collaborate. Email us at contact@mathtogether.ca. We can't wait to hear from you.